Okay, here's the second part of the guide sheet number 3. We're talking about energy, specifically mechanical energy, the energy of moving objects. And we're talking about it in terms of the two forms of kinetic energy and gravitational potential energy. Now, when we want the total mechanical energy of an object, we're just going to want to add all the energies it has together. We're going to sum them up. In this case, we're just talking about gravitational potential and kinetic. So the total mechanical energy of an object will be the sum, kinetic energy plus the potential energy, at any time during its motion. It's not the change, it's not the difference. We wouldn't subtract anything. We just want to add the two together at any point in time. Now, if the object moves in such a manner that we're going to conserve the total mechanical energy, then it's not that the individual types of energies stay the same. So not the kinetic energy stays the same, not the potential energy stays the same, and not the amount of the kinetic and the potential. It's the sum of the two that stays the same. So the total mechanical energy is conserved. Conserved here means stays the same. So we may lose potential, but if we do lose, in quotation marks, the potential, it will have been turned into kinetic. So as a total sum, we stay the same. If we're determining the total mechanical energy of these, you just want to sum the two together. This is the gravitational potential energy, so 3,000 plus 7,000 is 10,000 joules. Down here at this lower position, it's 5,000 plus 4,000, which is 9,000 joules. Up here, 40 plus 60,000 is 100,000 joules. And 50,000 plus 30,000 is 80,000 joules. Okay, now in both of those cases, the energy was not conserved. We went from 10,000 joules down to 9,000 joules. The reason that the energy will not be conserved is that work will be done by some kind of external force. In this case, friction and air resistance are the most likely culprits. Same thing in the second part. We lost 20,000 joules from point C to point D. If we have less amount of joules than we did at the start, they had to be taken away by something. The something that changes energy, again, is work. So work would have been done to create a change in the energy. In this case, since we lost energy, the work would have been negative. It most likely would have been caused by forces that acted against the motion, like air resistance and friction. Okay, we want to calculate the total mechanical energy of an object that's 5.2 kilograms. To calculate the GPE, it's going to be times 9.8 newtons per kilogram. And we're going to multiply that by the height, which is 5.8 meters above. We're going to have to add to that sum 1/2 of the mass, 5.2 kilograms, times its speed squared, 2.4 meters per second squared. Don't forget to square that. Squaring is the major impact on. Now, these are the numbers we used in guide sheet number 1. So this is 300 joules, and this is 15 joules, making our total mechanical energy being 315 joules. Now, if I round that off to inferiors, we're talking 320 joules for this particular case. Okay, in each of these cases, we're looking for what would happen to the kinetic energy. Will it stay the same, or will it go down? This is a down arrow. Will it stay the same, or can't we tell? And we're going to look at the kinetic, the potential, and the TME for each case. Now, if it speeds up or slows down, that's going to tell us what happens to kinetic energy. If it stays the same velocity, we should have the same kinetic energy. If it goes higher, we're going to increase the potential. If it goes lower, we're going to decrease the potential. Total is the addition of the two. All right, so a marble begins in elevated position and rolls down to the bottom of the ruler. Now, as it rolls down, we should get an increase in kinetic energy. But that kinetic energy can't come from nowhere. It came from a loss of potential. Now, that word loss is dangerous because energy cannot be lost or destroyed by ordinary means. It can also not be created by ordinary means. So it's not lost, it's converted into a different type. So it's converted from potential to kinetic. Assuming no friction or air resistance, then in our case here, the total would stay the same. Okay, a marble is rolling along a level table when it hits a note card and slides to a stop. The table is level, so the potential energy doesn't change, no change in height. But it slows to a stop, so we've lost kinetic energy, and that means we've got no gain in potential to counteract that. So that means the system is losing energy. The work of the force from the note card is causing it to stop. Cards pulled from the bottom of the incline to the top at a constant speed. Speed's constant, so the kinetic energy is constant. We're going up an incline, so the potential energy is increasing. The TME, therefore, has to be increasing or gaining potential without losing or having a reduction in kinetic energy. Okay, take a moment to go through the last four, see what you come up with, and then pause the video and restart and take a look and compare it to what I came up with, and be ready to ask any questions you may have about why I came up with what I did when you come to class. Okay, so in D, it's a constant speed, so the kinetic energy stayed level. It was going up a staircase, so the height increased, potential energy went up. That means the total energy of our person increased. In E, the mug accelerated, got faster in this case from rest, so the kinetic energy went up. The surface is level, so potential did not change. Therefore, the overall energy of the mug was increased by the force applied to it. Work was done to make it go faster. In the pendulum bob, it's going to go from rest to some higher speed at the bottom. That means kinetic energy increases. But in this case, the kinetic energy came from the fact that it was falling, going down, so the potential energy decreased. That leaves a conservation, the total mechanical energy being the same, assuming no significant air resistance or friction. In G, it's skidding from a high speed to a stop, so kinetic energy is going down. It's on a level road, the potential stays the same. That means the total work on this total energy of the system goes down. Again, work was done in this case by the brakes. That would be negative work. That would reduce the energy of the car, causing it to slow down. Okay, that's kinetic energy and gravitational potential energy and how they intertwine and change under various situations. We'll look a little more detailed at how work goes with that in our next episode.